Okay, hello. This is Dr. Janes, and today I'm going to show you how to make a portable. It's very portable. It's battery powered. I'm powering it with three of these 18650 batteries. Very high power, high voltage power supply using impulse transformers, induction coil transformers. Okay, so here is racing coils, some racing coils for race cars, and in this video I'll just kind of basically show you, I made a power supply similar to this before for powering my fuser device. So this is a 60 kilovolts back to back, so if you drive them out of phase, that's 120 kilovolts out of this little portable unit. Very cool. And do all sorts of different experiments with that, fusion or other things. So I'm going to show you most of how to do this. There's a video that I did separately for the other power supply, and I'll put those videos in the links on how to do the programming of the Arduino, which is kind of a separate project. I'm using the same program that I used in the other one, and some of the same techniques I used in my Sonic Blaster also. So I'll post some videos to that for the hardware of putting that together. And I basically show how to put this in the box and get it wired up. And you might need to see the other videos also to help you, especially with the programming of the Arduino. Anyway, the Arduino is the master oscillator that's controlled by these potentiometers inside this box. And anyway, this is what an Arduino looks like. Very cool. Programmable, analog and digital inputs and outputs. Very neat device, PIC processor. So anyway, let's get started. Very cool project here. Okay, so anyway, let's test out the high voltage portion of this guy. Okay, so we got our power box over here, and the high voltage transformer is there, and I'm going to keep them separated because, like I said, this thing does not like it when this thing starts arcing and stuff. So let's turn this guy on. And there we go. And I'm going to tune in the frequency. It's one of the most powerful, it has a certain bandwidth. This transformer seems to operate. Ow! I'm actually getting a shock off of this thing. Ow! I'll turn it up to full duty. And let's just try to draw some arcs off of this and see what happens. Oh, look at that. Holy crap. It shut down the Arduino even this close. That was like a couple centimeter long arc. Look at that arc. Wow. Yeah. Anyway, I haven't blown out my transistors yet, but very cool, huh? You can tell the voltage is pretty high. You might need to put a longer tether on it. See, it's starting to do discharge there. Wow. Anyway, make sure it's still working. Okay, anyway, this thing, when I'm running it sometimes, it gives me a little bit of a shock here. Unfortunately, these potentiometers came with plastic knobs, so I could put those on there and maybe not touch the metal box, and that will tell me, have a little dial where my potentiometer is pointed to. There we go. Beautiful, huh? Change the modulation. And we don't even have to touch the dials and get shocked. I think this is inducing such high fields that it's producing like maybe 100-volt impulses on here, which you can feel through your fingertips, unless I push them down really hard or something. So anyway, I think the dials look nicer. Very cool, huh? And again, those come with the resistor potentiometers that I ordered. I'll provide a link for that too. Anyway, there we go. Very cool. Our whole power supply. Okay, it looks like it has finally arrived, and let's take a look at what's in here. Okay, it's my FETs. Okay. Very cool. Always good to have spare FETs. Okay. And if you're interested, I'll post a link to these. These are the FETs that I'm using in my device right now. Okay. Very cool. Okay, so it looks like I finally got this together with everything working. I think the potentiometers, I was having problems with them for some reason. If I soldered them and they got too hot, it was destroying the wiper. Okay, so here we have our, maybe I'll turn these around so we can see them. Turn one of them around at least. Okay. So there is our neon light. I have these out of phase, and what happened? Okay, there we go. So the frequency's working. You can hear it doing different frequencies. So that's the carrier frequency, and here's the modulation frequency. I can do slow pulses. Okay, there I turned up the modulation a little bit. Okay, so I can change the modulation frequency with this. Okay, I can change the modulation duty cycle from a very short pulse to basically CW, almost CW. I couldn't, oh, there we go. And here is our duty for a carrier, so I can basically turn down the power by making the carrier pulse very short. And so there we go. I think our power supply is up and running, and I made this tethered so I could keep this away from that, because the circuitry in there does not like the fields produced by these things out here. And so I put it in a shielded box, and I put tethers on it so I can keep them far away from this thing. And again, these are my two Mallory coils, both rated for 60 kilovolts impulse transformers, high power. And very cool. So anyway, there is my device. And okay, so here's the first step in building my new power supply, and I'm using the same code and the same Arduino Uno that I used in my other high voltage experiment power supply that I showed in my tritium. Let's see. Let's get this out here. So there it is. I wanted to make a more compact version of that, just using one ignition coil. Just testing this one out. It's racing ignition coil. And I'm getting all the wires soldered up on the headers, same as I did on the other one. And so this is going to be the master oscillator, and it'll be able to generate some pretty fancy waveforms. Very cool, huh? So I'll be able to pulse modulate it and hopefully change the duty output as well. Okay. Okay, so here we go. I'm getting all the potentiometers hooked up, testing them all out, because I don't remember which one was which, so I'm reverse engineering that. And I got it hooked up to the scope, so we can see it pulse modulating. Okay. And it looks like it's working properly. So we have our carrier frequency and carrier pulse modulation. And let's see, this is carrier frequency, right? So we're just doing I'm just looking at the pulse modulation. So we can change the duty and the rate of modulation. Okay. And it's pulse modulating there. And let me just bring it up to there's the carrier level. So we can see Let's see. Come on, come on, come on. Okay. And I believe this is the modulation of the carrier signal. So see, I can make the carrier signal shorter pulses, less than square wave, so we can put less power into it. Or I can bring it up to full square wave. Okay. And here's a carrier frequency. So we'll try changing the carrier frequency. And there we go. So it's going up to higher frequency. So it looks like our device seems to be working pretty good. Okay, we're able to ready to go on to the next step, I guess. We've tested all these potentiometers and they all seem to be working. Okay, so here is, I'm building my new power supply. I'm trying to build a more compact and portable one. And let's just take a look. So I had a video that I did before, and I filmed making it, and then I did some revisions because I found out that the FET has wider legs than the 8-pin dip. And I really need something to hold the FET in. And that's with the ZIF connector. ZIF connector is great. You can just flip this lever and it will hold the FET in place. See, it locks it in place. And the dip doesn't need that. It kind of sticks right in that socket, and you can pry them out. But the FETs, they don't really have a socket that's good to hold them in. If you stick a FET in here, it's got a lot of torque, a lot of the circuit sticking out. It doesn't stay in there too well. So I haven't soldered this on yet, and so I watched my old videos because I'm trying to repeat my circuit that I made. I realized I should have probably done it better. And so here, let's take a look at the wiring, and I'll explain it a little bit. We have a capacitor here, and the capacitor is fed by, I didn't have red and black, so I used brown and white for positive and brown for negative. Okay, so this feeds the capacitor. This is electrolytic capacitor. And make sure you get the polarity right on that, or it'll blow up, burn out. And there's a bus bar here, and it's not connected to this bus bar, so I needed to put some wires under here, and it makes it a little bit dicey because this thing has to stand up above the wires, and so it holds it up high. It looks like the pins will barely go through, so I still can probably solder them through on the other side and get this circuit to work. But okay, so I'm connecting this bus bar to that bus bar so I can feed the IC down here. Now my other one, I didn't use a FET driver, but okay, so this FET driver, let's take a look here. Here is the data sheet, and it is a TC4420, which has only got a single input and 2 outputs. You can use either one, I assume. It's non-inverting. And I couldn't find my old chip that I used. Things are going to HEL, you know what, with all this communist takeover of the world, which I can't even talk about on this platform. So anyway, we'll just stick to the technical stuff. And so I'm feeding the bus bars, and I'm using them to provide voltage to our dip here. I haven't put it in there. I like to keep them out of the circuit while I'm soldering, so they're not subjected to heat or electrostatic, although I've never destroyed some with electrostatic. And so the positive bus bar goes up here. So this is the VCC, right? VCC is, or VDD, I guess they call it. And then the bottom ones here are ground, so I'm running the other one to ground. And I'm also connecting the ground to the ground of the FET, because remember, it's gate, drain, source. Okay. gate, drain, source. So the ZIF connector will hold the FET. I have a damping resistor between the gate and the drain of, I found a 2.2K. Before I used a 2.5. So anyway, I just thought it would be nice to have a look at the circuit before I put everything on here so you can see where all the wires are going. Okay, and here is the input to the FET driver. See, we got V in there and V signal in. I'll go over the circuit in a second. So it goes into the FET driver, and then I'm taking the signal out of the FET driver and putting it into the gate of the FET. So let's look at our circuit here. So here's our FET driver, the TC4420, and it's powered, hooked up to a capacitor, and I didn't draw a battery. There should be a battery there also powering that capacitor. So plus on the VCC, or VDD I guess, and minus on the ground. Signal comes in, comes out the outside, and then into the gate of the FET. I have a 2.2K resistor between the drain and the gate to stop some oscillations there. And then of course we have I'm going to use the same battery, but you can use a different power supply, higher voltage if you want, because this voltage does not have to match that voltage. You can put any FET, actually any FET will fit in here, so you can choose the voltage that you want to run at. Again, the source is connected to the ground of the whole system, the ground of the power supply, the ground of the FET driver. And then we can put our load, if we put another battery over here, or the same battery, which I'm going to use, it powers the load, drives the load, current through the load, goes through the drain, and then down through the source and returns to the battery. So it creates a loop like that. Because remember, all circuits are in a loop. And here is my rough circuit diagram that I just sketched out with our 4420 FET driver and whatever FET that we're going to use. Like, I can choose that later because I can plug anything into this once it's finished. And I guess the last step is to solder our cool ZIF connector onto this socket here. Make sure I solder these 3 pins, and I might solder another pin over here. I'm not going to solder everything. It's hard to unsolder it if you solder everything up, if you made a mistake or something. But the 3 pins for the transistor need to be soldered in, and then I'll probably solder the other corner to give it mechanical strength. And I think our circuit might be done. Okay. And so we'll combine this one with our other circuit over here, the oscillator circuit, and our high voltage coil. And I have some 18650 batteries. I use some of these, and a little battery holder, and I think we can make a nice compact high power unit for doing some cool experiments with. Very cool, huh? See if I can get the circuit and everything in there. Excellent. Wow, that is beautiful, huh? Okay, I had to abandon the FET driver because it was somehow messing up the Arduino. I think it was drawing too much of a load from it. So just testing out this new power supply. I actually took the coil off the old one because I wanted to compare it to the extra coil that I got. And they seem to be performing about the same, and I'm still in the circuit testing stage. But it looks like it's putting out quite a bit of power, and I don't have this super big ass capacitor that I had hooked up before, hooked up now. And it is definitely drawing some arcs. It seems to be locking up the Arduino though, so the Arduino might have to be shielded a little bit more. So I'll have to figure out what to do about that, because the Arduino doesn't seem to like those arcs when you start drawing them. Okay. Okay, so I think let's test this out. Oh, do I have some more here? Okay, what the heck's going on here? Okay, let's test this out. I have the thing modulated, And I have this capacitor hooked up so I can just touch it in and hook it in and bring it out. I think maybe because I'm using these awesome lithium ion batteries, they can put out so much power, maybe I don't need this capacitor here. It does not seem to be increasing the pulse power. Again, here we'll show that this thing is producing arcs. Okay, and I think that messed up the Arduino again. Okay, see, when I put the capacitor on there, it keeps the thing powered up for a considerable amount of time. So the capacitor actually is in the circuit, but it's really bulky and probably not necessary, so I think I might just pull this thing out. And that'll make my whole power supply much more compact. Okay. Okay, so here is my my oscillator circuit, and let's see. I think maybe I'll just put it here because there was some issues with that. So I have my Arduino as the oscillator, powering it with 3 of these batteries. I put 2 FETs in here with some heat sinks, so the ZIF connector is holding that in. Again, I abandoned the FET driver because it seems to be causing problems. Got my 4 potentiometers there. Have a neon light on the transformer so that I can't see the high voltage coming out. And let's take a look here. And it is producing high voltage. I got both coils hooked up. And the EMP actually interrupts the Arduino, so I gotta be careful with that. I'm gonna have to keep the Arduino away from the coils and keep it shielded. I have my 2 Mallory coils running in opposite phase, and see it's pulse modulated, so I'm pulsing it on and off. And let's see, MD. Modulation duty. So I can tune the duty up. Oh, it's causing havoc with my computer here. My computer does not like that. Okay. And what is this? Ouch. Is that thing shocking me? Uh-oh. Carrier frequency. Okay, that's the carrier frequency. Modulation frequency. There we go, so I can turn the modulation frequency down. Or turn it up. And this last one must be carrier duty, is that right? Okay, so the carrier duty can make the pulse more powerful or less powerful. So I can do all sorts of different types of modulation. Basically, this is like an amplitude. You can make the pulse very short. Very cool. Or very powerful, which is really messing up my computer here. Okay, I'll keep the power level down. Okay, again, I was tooling with this knob. Maybe the Arduino's having a problem. Sometimes it picks up some kind of flutter from the high voltage. Okay, yeah, my computer's really not liking that. Okay, so I'm going to try to put all this stuff into that box, and we'll see how that works out. Okay, let's take a look here. Yeah, I'll just bring this back further. So here I drilled some holes and put the pots into the top of our bud box. And just always like to keep on testing to make sure everything's working okay. Okay. Hello. Well, anyway. That's interesting. Oh. Okay, I got through drilling the holes in here and just testing out all the potentiometers. I like to make sure everything's working okay before I go on to the next step. Okay. And so we'll fiddle with this a little bit more. Okay, here we go again, and I always like to test things in stages as I move the stuff into a box. Again, this is the same power supply used on my fusion experiment a while back, but I wanted to make it more compact with the lithium batteries. And now I've got the switch through there, and always when you contort these wires, I got lots of wires. Probably be better if I use less stiff wires, but this is what I had available. And I've got it this far into the box, and let's give it another test, make sure we didn't break a wire or something shorting out or something. Okay, our device is pulsing. The frequency, the modulation, it's working. Modulation duty is now working. I had a problem. I think for some reason these potentiometers, if you get them too hot when you're soldering them, they break the sweeper thing in there. Potentiometer has a sweeper that sweeps across the resistor. And the duty's working, so all of our pots are working. And we're getting close to having this thing completely in the box. Very cool, huh? Of course, I put neon lights on both of these transformers so you can see that they're both working. Make sure everything's working, and it makes a buzzing sound as the power goes through it. Got the switch operable. Got the battery on the front, so it's easy to change the batteries. These are about 4 volts a piece, so 1, 2, 3. 3 times 4 is 12. I burnt these out if you run them higher than 12 volts, so don't do that. Okay. And we are very close to finishing this project. I have a lot of wires going up into here. I'm not sure if I can twist them all around and get them in there without having a problem, but we'll see. Okay, so I'll fiddle with this a little bit more. We'll see if we can get this all together inside of a compact little box. Okay. Okay, so again, more testing. I twisted the wires and got the box kind of on top. I haven't pressed it down yet. Just making sure I didn't create any shorts. Make sure all the potentiometers are working. Okay, looks like everything is working good. Very cool. I guess the final step, I'll try to turn off the power. You always want the power off when you're fiddling around with stuff. And we'll see if we can push it the rest of the way and get it closed without any shorts or breaking wires. And we'll have a neat compact device with high voltage. These should be 60 kilovolts a piece, so 120 kilovolts, hopefully. And much more compact than our old device over here. There we go. I had to take that apart a little bit to make this new one, but you know, if the power supply is more compact, and you're more likely to use it, it becomes more useful, right? Okay, very cool. Okay, so I finally got the box all the way down, and we'll give it a test. Okay. Oh, carrier frequency doesn't seem to be working. Okay, I'll have to take it back apart and fiddle with it and see what happened. Okay. Again, I made it so it's low maintenance, easy to change the transistors. So, hope you enjoyed this. Very cool power supply. Very dangerous. It's super dangerous. Don't get shocked by it. Anyway, this is Dr. Janes, and thanks for watching.